And first speaker is Lorenzo Aiello from Gran Sasso Science Institute. And he's going to talk about thermal compensation system in advanced and third generation gravitational wave interferometric detectors.
Two most important ones are two events that happened on August last year, when we observed for the first time a signal of gravitational wave from three different interferometers, the two American LIGO and the Italian Virgo 1, and then another event coming from a merger not of black holes but from neutron-star merger, with which followed an electromagnetic counterpart that marked the beginning of the gravitational waves multi-messenger astronomy. But when we speak about gravitational waves, what we are dealing with? Gravitational waves, and just to conclude, you know that last year the first detection marked the device variation turned to be awarded with the Nobel Prize in Physics. When we speak about gravitational waves, we are speaking about small perturbations in space-time, essentially in space, that are produced by the very strong and intense phenomena in the universe, as for example the merger of two black holes, two neutron stars, or explosion of supernova. But despite of the great intensity of this phenomena, their interaction with matter is extremely low. And this made the detection experimentally extremely difficult. They were predicted 1 century ago by the general relativity of Albert Einstein, but we need 1 century to detect them because a lot of technology challenge needed to be overcome in order to detect them. Why? Because of the extremely low interaction with matter, what we use to detect them is an instrument based on the interferometer of Michelson. And to detect them, we exploit one of their properties, polarization. Because gravitational waves, as you can see in this animation, stretch the space in one direction and compress the space in the other direction, and vice versa. Exploiting this property, we are able to use, if this works, okay, the Michelson interferometer, in which we have light that pass in two arms and then come back to this splitter. And so, when the gravitational waves pass through it, we have that one arm is stretched and the other is compressed. And so, at the detector, you have a change of the interference pattern. But when you say that these arms are stretched or compressed, what order of magnitude we are speaking about? We know that the variation of the length of the arms is proportional to the length of the arm itself and the gravitational waves amplitude. But because of gravitational waves amplitude are extremely small, and you are dealing with the interferometer with kilometers of arms long, what we have to detect is something of the order of 10 to the minus 18 meters. That, as you can recognize, is a very small quantity. The network of detectors that we have now is composed essentially by 4 great interferometers. The two American LIGO in Washington, Louisiana, in the United States, Virgo that is close to Pisa, here in Italy, and then we have also GEO that is in Germany, that is mostly used to validate technology for future generation of detectors. Then more detectors will join this network. The Japan Kagra maybe at the end of 2019. And then the LIGO India is scheduled to join the network 2012 and 22. About Virgo, what we have is essentially an interferometer, a Michelson interferometer with arms of 3 kilometers long. But then we have more and more objects that make the machine more complicated but more sensible to detect gravitational waves. I focus just to sake of simplicity on two stuff. The first is the use of oblivero cavities that are placed on the arms that allow you to make the light more travel along the arms. The light go many round trips inside it, and so the effective path length inside the arm is not 3 kilometers but 100 of them. And then you have a mirror called the power recycling that allow you to increase the power circulating inside the interferometer. Why I focused on this? I will show in a while, because that stuff are used to reduce the shock noise. And then we have as a source a neodymium laser that is shined up to 200 watts, and then another mirror that for now is not used, but it will use to tune the sensitivity of the detector. This is an example of sensitivity curve of an interferometer for gravitational waves. What does it mean? That all the signals that we have over this black curve, we are able to detect them. All the signals that are below it, we are not able because there are noise that are dominant over the signals. And we have the different type of noise are limiting us in different frequency window. At the low frequency, we have the Newtonian noise, the gravity gradient, that is the coupling of the mirrors inside the interferometers with all other mass around them. And the main source comes from the seismic surface waves. About the mid-frequency, we have the thermal noise due to vibration, mirror, and suspension. But about this, Diana after me will explain you more in more detail. And I will focus on shock noise that comes from the fact that light is made by photon, by discrete quantities. And in order to reduce them at the high frequency, we have to do two stuff: increasing the length of the arm of Rivero cavities, or increase the power that we have inside the interferometer, power recycling cavity. The point is that we have optics that are like this one, 40 kilogram of weight with a very high reflectivity, 35 centimeter of diameter, and with very, very value of absorption, 4.28 parts per million. The point is that the fact of this absorption is extremely low, is not zero. So, when you have a lot of power inside the interferometer and you want more and more in order to reduce the shock noise, you have that, for example, for 50 watts of input power that we are scheduling to use for the next observing run, you will have 250 kilowatts inside all the interferometer, and so you will have that around 80 milliwatts will be absorbed by the mirror. You can say, yes, it's a small quantity, but it's enough to rising thermal effects. Thermal effects are problematic because they give rise to the so-called optical aberration. Optical aberrations are generated by two different types of effects. The first is the one that I was telling you, absorption of optical power encoding substate of the optics. And then we also that so-called the cold effects that arise from imperfection in the production of the mirrors and their material. The more you increase the power, the more you reduce the shock noise, but the more you increase the optical aberration. And then we have two main thermal effects that we face. The first is thermal lensing. It's due to the fact that the index of refraction of our mirror changes with temperature. When you have a power absorbed, you have locally a variation of temperature. So you have a creation of a spurious lens, a thermal lens, inside the mirror. And then we have the thermoelastic effect that is due to the fact that a needed optic expands along the optical axis. So its radius of curvature will change from the nominal one. What does it mean, this? That we will have that the light will scatter from the fundamental mode on which we're working in higher order mode. We will have a loss of power, so we will have the signals to keep all the interferometers stable fainter. Then we will have less power inside our cavity. We will try to reduce the power to keep the interferometer work, but we will have less power in the cavity, and so we have a loss of sensitivity and of performance. In order to make the interferometer rightly working, we need to use a thermal compensation system that is used to restore the normal situation. The basic strategy is to induce in the optics another aberration equal but opposite in order to restore the nominal value and the nominal situation of work of the interferometer. In order to detect the aberration, we use this type of sensor that is, it seems difficult, but it's not. It's a CCD in front of, we have a OLED plate. In normal condition, you have a wavefront without aberration. and you have the light goes straight and results in a spotlight on the CCD in a specific position. And when you have aberration, this spotlight will change position. From this displacement, the sensor is able to identify and quantify the presence of the aberration. We do two different types of measurements. The first is the so-called on-axis, in which we go throughout the mirror, arriving at the high reflecting surface and go back. So we go inside it in order to detect the thermal lensing that is placed inside the mirrors. And then we do the so-called off-axis, in which we arrive with our probe beam with an angle of 45 degrees, then we go to another optics, and then we back to the sensor, and this is used to measure the variation of the radius of curvature of the mirrors. So, now we are able to detect the aberration. How can we correct them? Using actuators. We use mainly two types of actuators. The first is called ring heater, that is essentially a column nickel primes wires wrapped of physical silica ring, like this one, that are placed around the mirrors. They are heated via Joule effect, and when they are heated, their heating, their radiation, are able to reduce the radius of curvature of the mirror, restoring it to the nominal value. The second type of actuator are CO2 laser projector that emit a wavelength of 10.6 micrometers. This choice is not by chance, but it's because it's a wavelength that is optimally absorbed by the optics that we have in vehicle. The shining is not directly on the mirror, but an optics placed immediately behind it, an optics called the compensation plate, that allow to maximize the efficiency of the actuation. This is an example of the bench that we have to the compensation. We are able to shine three different types of actuation. The first is what we call essentially central heating. It's just a Gaussian beam and shining on the center of the compensation plane. The second one, the annular correction, is what we call the double hexagon system, because it's composed, as you can see, by two different annuli, one outer and one inner, obtained with hexagon. Hexagon is a lens with a cylindrical surface that allow you to transform a Gaussian beam in an annular one. And this type of correction is called the axisymmetric annular correction. And the last one, in order to compensate the residual aberration, we use what we call the scanning system. We scan the mirrors with a scanning pattern, a raster map made by 25 times 25 points. And we change the intensity of the actuation with a beam modulated with a pulse-optical modulator. What we have done on Virgo is a preliminary test of what if the actuators are right or wrong, in the sense if we are going in the right or wrong direction. In order to correct this, that I showed you the thermal lens, we channeled our DAS, our double hexagon system, and we observed the behavior of the field inside the interferometer with the increasing of the output power. You see that increasing the output power, the figure of merit that is called the gain of this field are progressively reduced. So you are making the interferometer worse and worse. So when we arrived at this value of input power, we activate our actuator and we observed an increasing of the gain of this field. Then we did some small tuning and we observed a further increase of the gain of this field. That is a proof that our actuator is working right. In the meanwhile, we are trying to investigate future actuator or how to improve the actual one. For example, regarding the CO2 laser, the point is that if you want to have a good actuation, you need to work with this type of laser. Gaussian beam, circular, almost perfect. This is the ideal world. The real one is this one. We often work with something like this, but not because of us, because it's the laser that sometimes change the working point. So the spectrum we already did the spatial filtering in order to improve it, and this is enough for advanced Virgo, could be enough, no more, for future actuator. So we needed to design what is called mode cleaner cavity. As said the name, Mode cleaner is essentially a device that allows you to clean the beam for all the higher order mode and restore it in a normal situation, the Russian built-in 001. The point is that for CO2 laser, we have no Faraday isolator that protects the laser for back reflection. And because of we are working with very high power, this back reflection could compromise the laser itself. So we try to develop what is called a triangular cavity instead of a linear one that is simpler, but shows back reflection. And another factor that we need to take into account is F. F is called the finesse, and is a parameter that say to you how much the cavity clean the mold, the laser. The higher is the finesse, the higher is the cleaning. The higher is the finesse, also higher is the difficulty to keep the cavity locked, in the sense that it works right. So you need to choose a trade-off among these two parameters. And then we found that a value of finesse around 100 is a good trade-off among cleaning and stability of the cavity. Moreover, we choose compactness in order to have a further easy installation and integration of this improvement of the actuator that we have already on advanced vehicle. Last but not least, the point is that to keep the cavity working, you have to use a standard technique called the Pandrive roll. But this technique assumes that the beam that you are working with is modulated with electro-optical modulator. Again, the problem is that for this type of laser, the electro-optical modulator are essentially out of budget. So we are trying to investigate for the first time a possible approach to keep the cavity resonant with, instead of electro-optical, acousto-optical modulator. And this work is still in progress. Last stuff that I want to show you is a future actuators for third generation that are deformable mirrors. Why? I told you that residual aberration are corrected with scanning system, but the problem is that scanning system could inject noise at the frequency in which advanced vehicle is sensible. Again, scanning systems are okay for advanced vehicle, but for future generation where you will have a more stringent requirement on the noise, could be good no more. So in order to avoid this problem, we will try to use the format of mirror that are used as DC correction to shape the laser beam. The deformable mirrors are made by many actuators that are activated, giving different type of voltage to the piezoelectric that is behind them. The mirrors that we are studying is this one that is 40 millimeter of diameter, but it is composed by 144 microactuators placed in 6 concentrical circular regions. And what we are trying to do now is an investigation of what I would call influence function, that is how much you change your wavefront, your phase profile, rising or lowering a single actuator. What I told you is not just in some sense for fun, but is something that is already studied for next generation. This is a comparison of sensitivity curve for different types of interferometric gravitational wave detector. You see that from the first generation to the present, the second one, toward the next one, we are trying to improve the sensitivity of a factor of 10, from first and second to second to third. And when a few months ago was presented the technologies for the Einstein telescope, the next third generation interferometric detector, speaking about thermal compensation system, this professor focused on two types of actuators. Deformable mirror, this one, bond cleaner, that are exactly what I showed you a few minutes ago. So, summarizing, we have finally detected after 1 century gravitational waves. Now our efforts are devoted to improve the sensitivity, the robustness of our detectors. But meanwhile, we have always to face wavefront aberration. But now we are able to face them with good wavefront sensor with dynamical actuator. Not forgetting at the meanwhile to looking forward to improve the present one and to look at new type of actuators. We are working now to the next observing run. We are here now in a commissioning phase for M4 Livingston LIGO and Virgo and also Geo. Commissioning means that we are pushing the interferometer toward the final working state. for the observing run that will start around the mid of February, it will be 1 year long. So this was I wanted to tell you now. You're still awake, so it's good. Thanks everyone for your attention.
Thank you, Lorenzo. There are questions?
I was wondering, when this device will be applied to the interferometry, how will you decide when to turn it on? Will you measure the decreasing power in the beam and then turn it on?
You speak about, for example, the double hexagon?
About
any actuators?
Yeah, actuators.
Yeah, the point is that you turn on all the machine and you see how it works. When you see that, for example, increasing the power at a certain point, the performance starts to decrease up a certain threshold, in which the machine is no more with the performance that you need to have, you at that point you said, okay, now I need this actuator, turn it on in this way. The point is that the commissioning is devoted to this process, in the sense in this month we are working with the machine on, and we are trying to find what is the optimal point for all the actuators, not only for the one of our subsystem, in order to be ready for the observing run, that when we will see a decrease of the performance, we already will know, okay, now we need this actuator with this certain value of work, in this sense. The point is that you always look at two figure of merit, in some sense, stability of the machine and performance. When you see that both one of them or both of them are decreasing for reason that you know, at that point you know, okay, they are decreasing for this reason, I need this specific actuator in order to restore the nominal working point.
Thank you.
You're welcome.
Any other questions?
I would like to know how much time the machine can go on with the improvement. So from one improvement and the next one, how long will we be working, the acquisition time?
Okay.
You can forecast how much time we have an acquisition. How long is the acquisition?
Okay, in order to have a general idea, before the end of the previous observing run and the start of the next one, it's 1 year and a half, more or less. Because of you need not only to installate and integrate the new actuators, but you need also to test if they are correctly working. And this is the aim of the commissioning. Usually the timeline is that you end an observing run, you allow some months of integration in order to allow all the subsystem to integrate the new improvements, the new upgrades, and then you restart commissioning for many months. In this case, we started in mid of March, and we will have the next observing run in mid of February. So you have close to 1 year of commissioning. And then you have, during the observing run, theoretically the situation is freezed, in the sense that all the subsystems are ready to do what they have to do. And so during the observing run you have theoretically no break. Could happen that the machine, for whatever reason, could, as we say, unlock, in the sense that it's working no more. But then it's not a problem, because you restart what we call the lock acquisition, in the sense that the machine automatically know how to back to work. And this is consider that you can have many days in which the machine work, that at a certain point unlock, but in half an hour the machine automatically know how to start to work again. I don't know if I answered your question.
Any other questions? Okay, just a curiosity. What is the maximum temperature that you reach by inducting the roller with the bigger coil to correct this aberration effect?
Temperature on the actuator or on the mirrors?
On the mirror.
The exact value I don't remember, but we are speaking about many tens of degree. I don't think up to 100, but
Okay, so 3000.
yeah.
Okay. So, if there are no questions, let's thank the speaker again. So, the next speaker is Diana Lumaka from University of Rome Tor Vergata, and she is going to talk about thermal noise reduction for future gravitational wave detectors.
Can you hear me? Working? Okay. Yes. Good morning, everyone. So I just show you a brief sum of my presentation that I will do. I will go really fast on gravitational waves description and interferometric detectors because you already heard something about that. Then I will go on more details about talking about thermal noise, what is thermal noise, in particular with what is causing thermal noise. And then I will show you the collaboration of which I am part, that is the Virgo-Potting R&D collaboration and the main research line. And I will go to the topic of my research, that is low-loss material mechanical characterization, showing you some results and a preparation procedure of the sample that we are going to use. From September 14, 2015, many things changed. Gravitational waves were detected for the first time, and many other signals have been detected during the last observational run. And also, as you already heard, the Nobel Prize was awarded to Weiss, Berish, and Thorne, part of the LIGO-Virgo collaboration. Gravitational waves are a prediction of general relativity by Einstein. General relativity was particularly new for the year because in this theory the gravitational interaction was no more considered as a force that acts on something, but as a properties of the space-time. The space-time that is perturbed by our gravitational waves that are ripples. When a gravitational wave passes, the distance, the proper distance between 2 points, free-falling points, change proportionally to the gravitational wave's signal that is named h. This kind of signal is really small if you think to neutron star coalescence in the near Virgo cluster. The gravitational wave signal is of the order of 10 to minus 21, and the corresponding variation in the distance between these 2 points is of the order of 10 to the minus 18, that is 1,000 of a proton's diameter. To detect a so small variation in the distance is not easy, and the winning strategy was to use an interferometer because in an interferometer we use light as a ruler. The two free-falling point that I was talking of before is represented by the two end masses, the two end mirror of the interferometer. And when gravitational waves pass, the two end masses moves. I mean, you will see in a minute. And what happens is that the interferometric condition at the output of the interferometer change, and say to us something happens, gravitational waves pass. Everything starts from a really simple layout. This is the Michelson interferometer, and became more and more complex to have a more sensitive detector. The point is that being so sensitive is sensitive also to a lot of noise sources. It's like if you are in a really noise party trying to hear someone singing a song. It's not easy because you have a lot of noise around. In fact, the interferometer detector is characterized by its own sensitivity curve, that is the black one. You already heard that it's characterized by different kind of noise in different ranges. You already heard about shot noise, how to reduce it, and I will focus on thermal noise in the mid-frequency range. So, what is thermal noise? It was 1828 when Brown observed for the first time thermally driven displacement of particle. It takes 100 years to have a mathematical description, a rigid mathematical description of the phenomenon, but now it is well known that in a system at thermal equilibrium, all the dynamical variables are undergo to fluctuations because thermal energy goes into kinetic energy. If one consider a ideal system, this translation, this variation in this modification in kinetic energy is specific of one frequency or some particular frequency that represents our mechanical resonances. If one consider a real system that has this fashion, this is no more true because the energy goes out the resonances and move around a certain frequency, and this is what we call noise. The spectral behavior of this distribution is related to the dissipation, the impedance of our system. So the thermal fluctuation that are our noise, the noise in which we are interested, are related to this dissipative part and represented by a damping coefficient. Damping coefficient that is related with external and internal damping. We will focus on internal damping of the system that corresponds to some friction inside the system. This friction arises from an elasticity in the system. What does it mean? That if we apply a stress on a system, the strain response of the system is not immediate, and the phase lag between the strain and the stress is represented by the mechanical loss angle, that is our damping coefficient that characterizes the system. Going to the specific case of interferometric detector, we have this fluctuation in the mirror surface that create noise in our detector. Obviously, higher is the internal friction, both in the coating and in the mirror substrates, higher is the thermal noise. We can see that the coating mechanical losses are several order of magnitude higher with respect to the substrate one, and so they are the dominant part of the noise. Here I report a simple formula of the coating loss angle, and we can understand from these which are the main strategies to reduce the coating loss angle. As you can see, we can try to act on temperature, going cryogenic, or we can reduce coating thickness or increase laser spot on the mirror, and finally we can also try to reduce the characteristic of the material that is the coating loss angle. Before going further, I want to show you the characteristic of the coating and of the mirror of the present gravitational waves detector that are the limit of our knowledge, is the best coatings that we are able to produce until now. So the high reflecting coating in gravitational waves detector are Bragg reflectors with fused silica and titanium doped tantala alternate layer, has low and high refractive index, and they are produced in the Laboratoire des Matériaux Avancés in Lyon, and they are really top level of coatings. They allow us to not lose more than 0.0001% of the light that impinge on them, because they have also an absorption lower than 0.4 parts per million and a scattering lower than 10 parts per million. So inside the Virgo collaboration, the necessity to reduce coating thermal noise has always been felt very much, and in the last period, our real collaboration starts to work hard on it. In the map you see all the laboratories that are involved both in Italy and France. and all the activities that they perform both in sample production and in sample characterization. Here you see a really brief summary of the main research line, and today I will show you the mechanical characterization, so the loss angle measurement of the coating materials. Because as I already said to you, we can try to reduce our noise reducing the coating loss angle. How can we reduce this coating loss angle? We can reduce it looking for something new that has that has this characteristic with a lower level, so we have to look for new material or new mixtures, or we can improve the mechanical losses research on the already known coating materials. In both cases, we have to consider that to make the measurement of the coating loss angle, we have to make a differential measurement. So we have to measure the loss angle of the sample itself and the sample plus the coating. Making difference, we can extract the value of the coating loss angle. You see the difference between substrate plus coating and just the substrate. So it is fundamental to well known and to characterize and prepare the substrate before the coating deposition. And this is particularly true for fused silica sample. I will show you in some slide why. Before, I want to show you also how to measure mechanical loss angle of the samples. The most used method is the ring down method that consists practically in exciting a resonator at a particular frequency and let it relax, measuring the relaxation time. Measuring the relaxation time, one can extract exactly the loss angle measurement of that particular mode. The best way to suspend disc resonators, so we are talking about disc samples, is the gentle nodal suspension, also known as GENS. Practically, the sample is suspended on its own center on a half sphere, and this is particularly good because we have no forces applied but the weight, and we minimize the contact area between the sample and the suspension, so we are minimizing the coupling between the two. Furthermore, it has a really high repeatability in the measurement and a statistical error of the order of 5%, and the coated surface are not damaged, and all the modes that has not a line that passes through the center of the sample can be measured, like the modes that has this shape. So let's see which are the issue of the fused silica sample. Since from the start, fused silica samples show a particular behavior in the distribution of loss angle in function of frequency. As you can see here, they are practically distributed on two different branches. On top, you see all the modes that are called butterfly and shows just azimuthal nodal line, so all modes like these two. While on the bottom, you see all mixed modes that shows both azimuthal nodal lines and radial nodal lines, as you see in the other two pictures. Furthermore, over this kind of behavior, they also show a aging effect. With time that pass, the the sample mechanical losses get worse. This kind of behavior can be healed in some sense with an annealing process. Also, if this kind of process is not definitive, because after other time the sample get again worse. So why the motivation of this behavior has been found in spurious dissipation coming from the lateral surface of commercial sample that is not polished, is raw, as you can see here. And so the sample losses is composed both by disc losses and barrel losses. So to reduce the losses of the sample, one has to eliminate, to cancellate the barrel part. To To do this, we design and realize a polishing facility for the barrel of the commercial sample. Here you see a picture of the Roma Tor Vergata CO2 polishing facility composed by a CO2 laser, a lens to reduce the spot of the laser on the barrel of the sample, two galvo mirrors that allow us to make different heating pattern on the barrel, and a rotary stage that rotates the sample during the polishing procedure. With this facility, we can make a lot of different set of parameters, optimizing time by time the polishing procedure. Other two procedures that are under study are annealing, as I already mentioned, that is heating the sample at a certain temperature, relaxing the internal friction of the sample, and vacuum storage, because from experimental observation, some deabsorption of the contaminants happen during vacuum storage. Now, finally, I show you some results. Here you see some visual and AFM measurement. After the polishing, you can see that the barrel is no more raw, but is polished. And after the polishing, the RMS value of the lateral surface goes from 180 nanometers to 0.7 nanometers. Also lower with respect to the surface of the sample. And here there is also the mechanical characterization of a sample. Here you see a fused silica sample of 1 inch diameter and 0.5 millimeter thickness. This is its first initial characterization. Here you see in pink the effect of an annealing process and the effect of vacuum storage. Both reduce the losses of the sample. Finally, this sample has been initially characterized to be further investigated annealing and eventually aging effect, and then it could be coated to obtain the coating loss angle measurement. This is another sample that I want you to show because this is its first characterization. This is the effect of CO2 polishing procedure, and this sample has been taken outside, stored in any particularly way, and after 10 months, it shows again losses of the same order of magnitude. So practically the aging effect is in some sense stopped or at least reduced. In any case, other investigation will follow, and further annealing will follow too, and also this sample could be coated. So, to summarize, the procedure consists in initial mechanical characterization and polishing and annealing procedure, a second characterization, and finally the coating deposition. Through the last, the characterization, one can extract the coating loss angle and characterize the material, different material. So, concluding, the characterization of fused silica sample is at a good point, showing good results in reducing both branching and aging effect, and annealing and vacuum storage are still under study. And obviously the CO2 polishing procedure could be optimized for sure, and we will work on it, but we are almost ready to characterize as much as possible coating material. So thank you for your attention.
Thank you, Diana. Time for questions. Does anybody have any questions? Okay, if not, I have a very simple technical question. I mean, it's more curiosity. What is the level of vacuum you use to store your sample?
So the storage is almost a casualty at the start. So we make the storage of the sample during doing other measurement of loss angle measurement. So the order of the vacuum is E-6